In this lesson, we're going to concentrate on end behavior asymptotes for graphs. We're looking at a graph to the right of f of x equals 2x plus 3 divided by x minus 1. We can see in the graph that there ought to be a vertical asymptote that has an equation x equals 1. And we can also see that there ought to be a horizontal asymptote with equation y equals 2. The vertical asymptote may be more obvious from the equation because we can look at the equation and say the denominator is equal to 0 when x is equal to 1. The horizontal asymptote, however, is not quite as obvious to us because this function is not in the form of a transformation of the reciprocal function, but it can be put in that form. In order to put it in that form, we're going to divide. So we're going to use three different methods. You can choose your method, but one of the methods for doing a division is long division, x minus 1 divided into 2x plus 3. When we do the long division, you divide the first terms first. So 2x divided by x is 2. Then multiply that quotient times the entire divisor. So 2 times x minus 1 is 2x minus 2. Then rather than subtracting, we change the signs and add that. And that will give us 0 plus a remainder of 5. So what that means is our function f of x can be expressed as 2, the quotient, plus 5, the remainder, divided by x minus 1. And you'll notice that that correlates with our horizontal asymptote y equals 2. And the reason that that correlates is because the remainder divided by the divisor is very small for values of x that are quite large, and large values of x can be found on the right side of the graph, and on the right side of the graph, the y values are approaching 2. Now the same is true for values of x that are very negative. When they're very negative, the y values are also approaching 2 because that remainder piece is getting very, very small, or rather the remainder divided by the divisor is getting very small. Now there are other methods to do a division, and when you have a division in the form x minus a number or x plus a number, you may use synthetic division, and that may be preferable to you. We put the 0 of the divisor, 1, in the box, and then the coefficients of the dividend, which are 2 and 3, right next to it, skip a line, and then bring down the 2, multiply that by 1, and we get 2. I'm going to write that underneath the next number, and then add, and that gives us our coefficient for the quotient, and it also gives us the remainder, and that's going to give us the same result here. We write the quotient plus the remainder divided by the divisor. There is a third method, and the third method is a little bit of sort of clever thinking. So 2x plus 3 divided by x minus 1 would be evenly divisible if the numerator were, instead of 2x plus 3, 2x minus 2, because then 2x minus 2 would be factorable, and then we could just factor and cancel. So I can make the numerator into 2x minus 2 by subtracting 5. Now we have 2x plus 3 minus 5, which is 2x minus 2. But since we can't just subtract 5 from that numerator, I'm going to add the 5 back. And then I'm going to do a grouping here and rewrite this fraction as 2x plus 3 minus 5, which is 2x minus 2 divided by x minus 1, plus 5 divided by x minus 1. The 2x minus 2 will factor, and we can cancel our common factors of x minus 1, and that will give us the same result that we got before from the long division, 2 plus 5 divided by x minus 1. You can take your pick of methods. We'll see later that the synthetic division may not always be used, but these other two methods can usually be applied fairly easily. All right, now we're going to consider a function that is not a transformation of the reciprocal function. And on this one, we can see that vertical asymptote again in the graph. And that vertical asymptote has an equation, x equals 1, vertical line. And that's fairly easy to see from the function. X minus 1 is the denominator. When x equals 1, the denominator is equal to 0, so the function's undefined. However, it doesn't have a horizontal asymptote. What it does have that we can kind of see from the graph here is a slant asymptote, which we will refer to as an oblique asymptote. And you'll notice that the oblique asymptote has a y-intercept of 1 and a slope of 1, which means that its equation is y equals x plus 1. Let's go back to our division, and we're going to take that same function g of x and write the division x squared minus 2 divided by x minus 1 in 3 different ways. To use long division, we'll divide x minus 1 into x squared plus 0x minus 2. We have to put that 0 placeholder in the middle for the x term. First term divided by first term is x squared divided by x, which is x. Then we can multiply the entire divisor by x. X times x minus 1 is x squared minus x. Now change the signs of the x squared minus x and add, and that gives us a remainder of x, and then we can bring down the minus 2. Next step is first term divided by first term, which is x divided by x, which is plus 1. So plus 1 is the next term in the quotient. And 1 times x minus 1 is x minus 1. And then we're going to change the signs and add. And we're going to get a remainder of negative 1. So what that tells us is that g of x can be rewritten as x plus 1, the quotient, plus the remainder, negative 1, divided by the divisor x minus 1. The same thing that was true before is true about this function. This remainder over divisor piece is going to get very small when x is either very positive or very negative, and so there is an asymptote to the graph in the form of y equals x plus 1, just the quotient part of that function. We can do the same division using synthetic division. Let's demonstrate that right now. We put 1, the 0 of the divisor, in the box, and we're dividing into 1x squared plus 0x minus 2, and then skip a line, bring down that 1. 1 times 1 is 1. Add that column. 1 times 1 is 1. Add that column. And these give us the coefficients of the quotient, 1x plus 1, and the negative 1 gives us the divisor. So that's going to give us the same result. The third method, again, requires a little bit of clever thinking. Instead of an x squared minus 2, it sure would be nice if the division had x squared minus 1 on the top. That way we could factor x squared minus 1 into x plus 1 times x minus 1 and cancel common factors. So I'm going to add 1 to the numerator, and we have to acknowledge that I can't just add 1 unless I subtract it again. So now I'm going to group this piece together, and that will give us a result of x squared minus 1 divided by x minus 1 plus negative 1 divided by x minus 1, and the x squared minus 1 factors to x plus 1 times x minus 1, cancel common factors, and that will give us an x plus 1 plus negative 1 over x minus 1. So same result that we got using the long division. In the next function, h of x, we can take a look at its graph and notice that in this particular one, we definitely have a horizontal asymptote here because we can see the ends of the graph are getting closer and closer to a y value of 3, so the horizontal asymptote is y equals 3. And this function apparently has no vertical asymptote, and the reason it does is because x squared plus 1 can never be equal to 0. Now that's just true for all real values. If x squared plus 1 were equal to 0, x squared would have to be -1, and then x would be an imaginary number. But for purposes of graphing, we're only talking about real numbers. So let's do our division again. This time, I can't use synthetic division because we have a quadratic divisor. It's not in the form x plus a number or x minus a number. Since we have an x squared in the divisor, that means that long division and that other technique are the only ones available to us. So let's go through the long division. X squared plus 1 divided into 3x squared plus 0x plus 0, putting the 0 placeholders in there. And then first term divided by first term, 3x squared divided by x squared is 3. Multiply the 3 times the entire divisor, and we get 3x squared plus 3. Now I'm going to change the signs of both of those to negative, and then add, and that'll give us a remainder of 3, which means that our function h of x can be rewritten as the quotient 3 plus the remainder -3 divided by x squared plus 1. As in the previous examples, the remainder over the divisor gets very small as x gets either very positive or very negative, and so there is an asymptote to the graph in the form y equals 3, and we're going to call that an end behavior asymptote. There is another method for division that we can use, and so I'm going to rewrite the fraction 3x squared divided by x squared plus 1. It sure would be nice if we could factor the numerator, and so if we had a plus 3 added to that, then we could just factor out a 3, and 3 times x squared plus 1 divided by x squared plus 1 would be 3. But I can't just add 3, so I'm going to subtract it back and then do a grouping of the 3x squared plus 3 together, and this fraction will be equal to 3x squared plus 3 divided by x squared plus 1 minus 3 divided by x squared plus 1. The 3x squared plus 3 can be factored and cancel common factors, and that will give us a quotient of 3, and then minus 3 times x squared plus 1. So that gave us the exact same result as the long division, so pick your method. This brings us to a more substantive definition of what constitutes an end behavior asymptote. So end behavior asymptotes are either going to be one of two types, horizontal or oblique. That's a non-horizontal line that is not vertical. And that's determined by dividing. As the values of x approach a positive or negative infinity, the value of the remainder over the divisor approaches 0, and y values approach the value of the quotient. So we can find those end behavior asymptotes by dividing. In example 1, we're going to perform a division, and then we're going to use the results to determine the equations of all asymptotes to the graph. Let's determine vertical asymptotes, however, first, because the vertical asymptotes don't require dividing. We just need to look at our denominator, and if x plus 3 is equal to 0, then x is equal to -3. So this function has a vertical asymptote x equals -3. Now I'm going to do division. I'm going to choose synthetic on this one because we have a divisor that's in the form x plus a number or x minus a number. The 0 of the divisor goes in the box, and then the coefficients of the dividend, which are 1 for the x squared term, 1 for the x term, and 0 for the constant term, go right next to it, skip a line, bring down that 1. 1 times -3 is -3, add that column. -2 times -3 is +6, add that column. And so this gives us a way to express f of x after dividing, and that re-expression is 1x minus 2 plus the remainder 6 divided by the original divisor. Just as before, the horizontal asymptote can be written using the equation of just the y equals the quotient. So that gives us an oblique asymptote, not a horizontal this time, because y equals x minus 2 is not a horizontal line. So y equals x minus 2 is an oblique or end behavior asymptote to that graph. No horizontal asymptotes. In B, We can also determine that there is a vertical asymptote by setting that denominator equal to 0. So our vertical asymptote is x equals 4. And then we can use our division. I'm going to use synthetic division again. The 0 of the divisor, x minus 4 is equal to 0 when x is 4, goes in that box. And then the coefficients of the dividend, which are -3 for the x term and 10 for the constant term, go right next to it. Bring down that -3. -3 times 4 is -12, and that gives us a -2 divisor, which means that g of x can be re-expressed as the quotient -3 plus the remainder -2 divided by the original divisor, x minus 4. Y equals just the quotient part is the end behavior asymptote. In this case, y equals -3, and that would be a horizontal line. In C, we have a special example here because x squared plus 4 is only equal to 0 if x squared is equal to -4, and a square cannot be equal to a negative number if x is real. So there is no solution, which means there is no vertical asymptote here. We're going to do our long division. So doing the long division, x squared plus 4 goes into x. And you'll notice that first term divided by first term doesn't go evenly. There is no way to divide x by x squared and get a result that's not a fraction. So x divided by x squared goes 0 times. So that means that this function is already in the form where it has the remainder x over the divisor x squared plus 4, and we can always tack on a plus 0 there, which means that there is a horizontal asymptote in the form y equals 0 for this graph. So when the numerator is not divisible by the denominator, or the numerator's degree is less than the denominator, there will be a horizontal asymptote for that rational function in the form with the equation y equals 0. Okay, last example for this one. If we think about our vertical asymptote here, it would be better for us to think of this in factored form, x plus 1 times x minus 1, and then you'll notice that x is equal, the denominator is equal to 0 in two values of x. So our vertical asymptotes, there are two for this graph, x equals -1 and x equals +1. Now doing the division, x squared minus 1 divided into x squared plus 0x plus 0. So first term divided by first term, x squared divided by x squared is 1. 1 times the entire divisor is x squared minus 1. I'm going to change the signs and add, and now we have a remainder 1. And so this function can be rewritten as f of x is equal to 1 plus the remainder 1 divided by x squared minus 1. The quotient part of that gives us what y equals for the end behavior asymptote, and that'll be y equals 1. And y equals 1 is a horizontal line. No slant asymptote this time. Notice for this one that, again, long division is the only way to do this since we have a quadratic divisor.